Welcome to the team. Seriously, if you're a junior developer just stepping into AI architecture, there's this one universal pain point you are literally guaranteed to hit immediately. It's building a seemingly perfect retrieval system that somehow just totally fails your users. You've indexed all the documents, you've set up the vector database, the whole shebang, and yet the results come back completely empty. Well, in today's explainer, we're going to fix that by bridging what's known as the semantic gap. So the inciting incident of our system's journey, the whole reason this happens, starts the exact moment a user types in a weak one-shot search request. And man, it is incredibly frustrating when your database holds the absolutely perfect answer, but the retrieval mechanism just completely misses it. But here's the kicker. The culprit isn't the database, and it's definitely not your documents. Actually, the culprit is the query itself.
And that brings us to the semantic gap. Think about it. A user is usually in a rush, right? So they just type slow DB. But your pristine, heavily optimized technical documentation doesn't use those colloquial words. It uses complex hierarchical structures and dense terms like database query latency or indexing bottlenecks. The user's intent matches perfectly, but the vocabulary, it's just completely misaligned.
To build a highly optimized retrieval pipeline, we'll quickly map out the semantic gap problem, look at the tools for query expansion, wire up the optimized pipeline, balance those tricky architectural trade-offs, and then wrap up with some advanced best practices.
All right, Section 1, the semantic gap problem. Let's see what actually happens when we just leave this gap unaddressed.
If you rely on a basic, single-step workflow without any expansion, it's basically a recipe for low recall. You're going to miss highly relevant documents and end up generating really weak, unhelpful answers from your LLM. But by upgrading to a multi-step workflow with query expansion, we cast a much wider net. The system grabs better coverage, better context, and honestly, vastly superior accuracy. It's a real game changer.
Moving right along to Section 2, types of query expansion. Let's dive into the specific tools we use to actually execute this.
Now, before we start engineering the pipeline, let's establish a firm baseline. Query expansion is simply rewriting or enriching the user's initial query to improve retrieval recall. And by recall, I mean the system's ability to find all those relevant documents hiding in the dark corners of your database.
I really want you to keep this core mental model in your head as we go. We aren't changing the user's intent. Not at all. We are simply asking the exact same question in much smarter ways. This approach acts kind of like a planner, drastically reducing errors compared to those raw one-shot requests. It's essentially a translator, bridging a rushed human thought and a strict literal index.
So our arsenal breaks down into 4 main types. You've got synonym expansion for those simple vocabulary fixes, semantic expansion, which uses an LLM to really enrich the query, multi-query expansion to generate several variations of the same question, and context-aware expansion, which cleverly leverages domain knowledge or the user's search history.
Let's look back at our anchor example using the LLM-based semantic method. A user throws us 2 lazy words, slow DB. The LLM steps in and translates that into a rich, highly searchable string like database performance issues, query latency, indexing problems. Bam! Suddenly your vector database has exactly what it needs to find a real match. We can also use something called query decomposition, which gives us a fantastic list of actions for effective task decomposition. We take a broad question like, why is the database slow, and break it down into a step-by-step sequence. Step 1, search for indexing issues. Step 2, query optimization. Step 3, locking problems. It literally forces the system to systematically check every single technical variable. Okay, Section 3, building the optimized pipeline. Let's look at how we actually wire this up in the codebase.
This orchestration flow is absolutely essential for building scalable, hierarchical intelligence systems. First, we expand the original query multiple times. Second, we fire those queries off in parallel to retrieve our documents. Third, and this is key for keeping your context window clean, we merge and deduplicate. And finally, we re-rank that unified list so the absolute most relevant information is sitting right there at the time. Now on to Section 4, balancing pipeline trade-offs. Because look, in a production environment, this multi-step journey definitely comes with a cost.
It's a really delicate system balance. Pushing your expansion size definitely increases your recall, but it actively decreases your precision by pulling in a bunch of junk. Increasing the number of queries, that boosts your coverage, sure, but it spikes your system latency. And giving your LLM a massive context size means more info, but your token costs are going to completely skyrocket.
So if you just expand blindly without a solid strategy, your system is going to choke on three major challenges. Overexpansion will flood your LLM with irrelevant noise. Ignoring latency leaves your poor users staring at a spinning loading wheel. And redundancy? That just wastes valuable processing time analyzing the exact same document over and over.
Finally, Section 5, Best Practices and Advanced Techniques. Let's dive into how to avoid those pitfalls with some production-grade strategies.
To build a truly robust system, you must always pair your expansion with a re-ranker to protect your precision. Also, combine your vector search with traditional keyword search to catch those exact matches. And please, aggressively cache your expanded queries. You never want to pay that LLM latency tax twice for the exact same search.
Now, when you're tuning parameters like search depth, your absolute sweet spot is typically 3 to 5 expanded queries. This perfectly balances the need for maximum document coverage against the harsh realities of database latency. Honestly, anything more than 5, and your system just slows to a crawl for seriously diminishing returns.
Advanced architectures visualize this whole workflow as a high-speed journey through a complex information space. You can build iterative loops, pull initial documents, let the LLM read them, expand the query based on that new knowledge, and pull again. You're basically creating a system that constantly learns and auto-improves over time from its own bad queries.
At the end of the day, query expansion fundamentally fixes the query, which improves absolutely everything downstream. It leaves us with one final, pretty provocative question for your engineering team. When retrieval fails because of a weak search, are you going to waste cycles trying to rewrite perfectly good documents, or are you going to just fix the queries themselves?